Okay, I think we can start now. Our next speaker is Cleonice Bracciali, which is a professor in Universidad Estadual Paulista in Brazil. He's going to present us her work, relation between a class of Sobolev orthogonal polynomials on the unit circle and a subclass of continuous Hahn polynomials. Cleonice, thank you very much for the presentation. You can start.
Thank you, Luis. And first of all, I would like to thank the organizers, Diego, Luis, and Felipe, for the invitation, for this opportunity to speak here today. Actually, this work is a joint work with Jéssica da Silva. She is a PhD student of us, and my colleague, Ranga. We are all from UNESP, Universidade Estadual Paulista. Actually, let me change here. So before talk about Sobolev orthogonal polynomials on the unit circle, I needed to define a positive measure, mu here on the unit circle, t, the notation. We are going to consider and denote by phi n, the sequence of monic orthogonal polynomials on the unit circle. That means this inner product, we are using here theta from 0 to 2 pi. This inner product is 0 when n is different of n, of course, you know. And we are going to denote here by an, mu, respect to mu, the inner product when we use the same orthogonal polynomial here, phi n. For Sobolev inner product, we need two probability measures on the unit circle. And the Sobolev, we are going to do the Sobolev inner product that we are going to do here is going to be given like this. S is the notation for the Sobolev one, is composed by the inner product, involve the functions for the first measure, mu0, plus SS is a positive parameter, and the derivatives of the functions in the inner product with respect to the second measure, the inner product defined here. We are going to denote by capital psi n here, the monic orthogonal polynomials with respect to this inner product. So we call them Sobolev orthogonal polynomials on the unit circle. We know that in the real line, there are many studies about orthogonal polynomials with respect to inner products on the real line. I mean here, they can define by this using mu0 and mu1, here also the derivatives, where they are measures on the real line. And also when these two measures has actually this property here, the orthogonal polynomial with respect to the first measure, mu1, can be written in terms of the derivative of two polynomials, of the two orthogonal polynomials with respect to mu0. When the orthogonal polynomials has this property, this pair of measure were called a recurrent pair of measure. This concept was introduced by Earles and others in 1991. And after this paper, there was a lot of studies about these polynomials on the real line. But in the unit circle, not so much studies until now. But for example, Amilcar, Ana, Paco, and Maria das Neves in 2008, they used this concept of coherent pair of measures, and they get interesting examples on the unit circle for this kind of orthogonality. But what we are going to use today was another concept used actually by my colleague Ranga in 2016. He used a coherent pair of measures of second kind. What we mean here by second kind? We have two measures again, now on the unit circle, and now the derivative of one orthogonal polynomial here with respect to the first can be written in terms of two polynomials, orthogonal polynomials with respect to the other one. Here was one written in terms of two derivatives. Here we have one derivative written in terms of the other. So when these two measures, when the orthogonal polynomials of these two measures satisfies this relation, we will call them current pair of measures of second kind. In 2017, Paco and Ranga, they characterize all the pairs of measure that has this characteristic, and they find actually three different families of a pair of measures that satisfies this, and they also study the Sobolev orthogonal polynomials. Today we are going to deal with one of these classes, because this the title of the talk is a class of Sobolev. So we are going to deal with the following measure. Take lambda greater than half, eta a real number. We are going to actually use this notation. B is equal to lambda plus I eta. And we consider the measure mu b given such that this inner product is given here. And here we can see the weight function, the measure mu b. Mu b here, we put this parameter here, tau b, that to make the measure a probability measure, okay? You see that it depends actually of lambda plus eta. So in these two papers, they deal with also another measure that is a modification of mu b, where they take a parameter epsilon between 0 and 1, and they created this measure mu b epsilon, that is exactly mu b plus a mass on the point 1 here, of size epsilon. And the Sobolev inner product that you are going to use is the following. For S positive, the first measure here, the one that involves the function, are the measure mu b epsilon, like this one, and the second measure is mu b plus 1. For our notation, we are always called psi n, the Sobolev orthogonal polynomials, the monic Sobolev orthogonal polynomials. Phi n b will be the monic orthogonal polynomials with respect to phi b, and phi b epsilon with respect to mu b epsilon. It's known that the orthogonal polynomials with respect to mu b is given in terms of the hypergeometric function. Actually, is related to what Luke told before, and it was given in the work of ASCII about the collection of Zegus papers. And in 2010, Ranga used this notation, and he got this way. He used this notation. Then also in a paper in 2013, they gave an expression for the orthogonal polynomials with respect to mu b epsilon in terms of the polynomials Rn here that also are hypergeometric polynomials. Actually, these polynomials are related with para-orthogonal polynomials on the unit circle. And here they wrote these new polynomials, and here they use these coefficients that I just need to explain. This mn here appears because the polynomials BR are sorry, R and B are related with the positive chain sequence denoted by dn plus 1 lambda, given in this way, the same lambda greater than minus half. It's well known, this is the request relate the positive chain sequence that appear, for example, in the Gegenbauer polynomials. And it's known the minimal and the maximal parameter sequence for this chain sequence. The minimal, we denote by here ln, it's given this way. The maximal is written in this way. Actually, it means that the chain sequence can be written in terms of this minimal parameter sequence in this chain way, and also can be written in terms of the maximal parameter sequence. In that paper in 2010, with the introduction of the modification with epsilon, Ranga defined another chain sequence that he denoted by dn lambda epsilon, where d1 is given in terms of epsilon and m1, and the other elements of this sequence is the same given here. He proved that the minimal parameter sequence, of course, when m0 equals 0, we are talking about the minimal parameter sequence. And the other elements, parameters, is written in this way. So the parameter, the coefficient that is here is the minimal parameter, the parameters of the minimal parameter sequence given here. Okay, let's come back to the unit circle and about the coherent pair of measures of second kind. In this paper, actually, it was proved that the derivative of the orthogonal polynomial with respect to mu b epsilon can be written in terms of the orthogonal polynomials of mu b1. So mu b epsilon, mu b1 form a coherent pair of second kind because they are exactly the measures used in the Sobolev inner product of the unit circle. From this property, actually, the best way how to use this was get that the Sobolev orthogonal polynomial with respect to this inner product can be written in terms of the orthogonal polynomials of this measure. But we have here two Sobolev polynomials can be written in terms of one. So when we know information about these coefficients, we can get more information about the Sobolev. Actually, these coefficients beta, they are called connection coefficients, and in this paper, they were given by this recurrence here. They prove that beta 1 equals to 0 because they are harmonic both, and beta n plus 1 can be written in terms of beta. Here, these coefficients Q and P, and here are given in terms of the Cayenne. Cayenne is the coefficient in this relation here. Also, it's given in terms of the inner products when we use the same orthogonal polynomials. Involve the measure mi b plus 1 and the measure mi b epsilon. It's this inner product is explicitly given in terms of Hahn symbol, and the other depends, of course, of epsilon, and also depends of the minimal and the maximal parameter sequence. So all until here is just the background, the results that we need. Now we are going to think about how to relate actually the coefficients beta with a polynomial that I'm going to call here Qn b epsilon. First, we are going to make a trend. We are going to tell that the S, the parameter in the Sobolev, will be written as a kappa over Y. We'll define this kappa later, okay? So now we are talking about some betas that depend on kappa and Y. Y also positive. The idea is here just to change the S that we have that before, and now we have S over kappa over Y here, and if we multiply by Y both sides, we see that Y times Q will not depend on Y. That's the idea. Okay, from this property, from this way, how to write the betas, we can suppose, we can first assume that beta n plus 1 can be written as a fraction of two polynomials that depend on Y, exactly the Y that we have here. So suppose this, and also we will start with Q0 equals to 1, and just using this property, we realize that the polynomials Q and B satisfies this property here involving Q and Pn. Now, what we have done is we use the value of P here, and we multiply both sides by Y over the norm, the inner product, that different from 0. And because this property here, this Y here, we get actually Y plus a coefficient here. So we see that we have a polynomial here, a polynomial in Y. See? Here, remember, Y times Q does not depend on Y, because in Q we have Y on the denominator. So we have here the three-term recurrence relation. Actually, with the initial condition, we can just assume it Q0 equals to 1. But here we need another step. We multiply that three-term recurrence relation by this quantity, and we get a new one, but we are going to call this polynomial, since we see that here we have just Y, we have a harmonic polynomial. So we are going to call this polynomial here, see, we have n minus 1, n minus 2, we call it the sequence of a polynomial Qn hat. Qn hat means that is the monic polynomial. So now, just making this definition, we have this three-term recurrence relation. Remember that we have to decide who is kappa. So if we choose this, if we make this choice for kappa that it depends on B, when I tell it depends on B, it depends on lambda and eta, and also epsilon. In this way, and actually this is positive. Now, with this choice, this multiplication, for example, here, and we know this explicitly, these values, we get here a more simple coefficients that we call it n minus 1, and just remember that it depends on lambda and eta. Also, the multiplication of this by this, I wrote here, just using all the information again. It's actually this that we are going to call it a coefficient Cn minus 1. And finally, this last one will be written, it's this value, but if we see, it's actually the An minus 2 here multiplied by Cn minus 1 here. Okay, what we get? We start with beta, and we get now a sequence of monic polynomials that satisfies this three-term recurrence relation. with these coefficients. The interesting thing is, although we call it a Q that depends on B, if we use these coefficients, we see that this polynomial does not depend on eta. So these polynomials, when they are harmonic, they depend just of lambda. So let's now write the new information about the coefficients beta. Remember that we wrote the monic polynomials as this, and at the beginning we suppose that beta is written in terms of q n minus 1 over qn. So we just can also use our choice of kappa here, and we denote this coefficient by capital Cn here, and using the values of kappa, we see that this coefficient can be written in this way. And we see now that these coefficients depend on eta. Although the monic does not depend on eta, this depends, but this can, when we multiply this, we erase this dependence. So now, instead to write beta in terms of q, we are going to write betas in terms of q hat, because we have the recurrence relation. Just to make the substitution here, qn minus 1 is qn minus 1 hat over capital Cn, and the opposite here, and we get this new information. Let me just make a summary what we have until now. We have the Sobolev orthogonal polynomials written as 2 Sobolev, can be written as 1 orthogonal polynomial. The connection coefficients here now can be constructed by this fraction, where the polynomials q and hat here satisfies this equation, this three-term recurrence relation. And finally, now we can make the connection with continuous dual Hahn polynomials. But we managed to do this connection just for epsilon equals to 0. When epsilon equals to 0, we are talking about this polynomial qn hat lambda 0, which means that if we come back in the information about the minimal parameter sequence and the maximal, when epsilon equals to 0, that minimal parameter sequence actually is exactly the maximal parameter sequence, and we know it explicitly. So we just substitute here by the explicit formula, and for the case epsilon equals to 0, we get these coefficients, and if we substitute, we have this polynomial, the polynomial given by this three-term recurrence relation. During our studies, actually, during the studies of Jéssica, our PhD student, and we were thinking about student, can we realize which or these polynomials are some non-polynomials? So after some research, we come across that these polynomials are related with continuous dual Hahn polynomials. Just to me remember here, what are the continuous dual Hahn polynomials? I use the same book that Professor Luis used before. We have here that the continuous dual Hahn polynomial can be given in terms of 3f2 hypergeometric function. It depends on 3 parameters, A, B, C, satisfies this recurrence relation, where the parameters are given here. For dual Hahn, the continuous dual Hahn polynomials, either A, B, C should be all positive, or A can be negative, but then A plus B and A plus C has to be positive. So we have three parameters here. We make this choice. Remember that our Sobolev polynomials depend on lambda, that's greater than minus half. Then we choose the parameters in the continuous dual Hahn polynomial S. A is half minus lambda, B is half plus lambda, and C is 3/2 plus lambda. So just we change the notation here. We are calling Hn lambda, the continuous dual Hahn polynomial with this choice. It's known that they are orthogonal on the positive part of the real line. The norms given here. And also here is interesting because it's orthogonal with respect to measure. When lambda is in this interval, this means that A is positive, so it's orthogonal with respect to continuous weight function. When lambda is greater than half, we have the case A negative, and then we have the continuous part plus the some mass point here. The weight function that is here is given like this, and the mass here is given like this. So let's now see the two recurrence relation together. I put here the Hahn polynomial, the recurrence relation for the Hahn polynomial. And here, the recurrence relation of the polynomials that we get, the Qn hat lambda 0, epsilon equals to 0. So now it's quite easy to see. We have here we have the same coefficient. Here we have minus, here we have plus, and the Hahn polynomial has this added term here we can see before. So the Hahn polynomial can be given as -1 to n, Qn hat of minus x, because this different here, and minus this quantity here because this. That is the relation that we got, and one of the main results of this talk. Actually, we tried to find if these polynomials, when epsilon is not different from 0, are some orthogonal polynomials known, some non-orthogonal polynomials. We don't know yet. But the recurrence relation for this Q that help to get the connection coefficients beta are very useful. Another thing that we can see this, we know that the zeros of the continuous dual Hahn polynomials are positive. They are orthogonal on the positive side of the real line. So because this, the zeros of Qn hat will be negative. And this is very well, it's good because remember that beta is defined by a ratio of this Q. But now our choice is actually S is positive. Our choice of kappa will be this, and also positive. So Y here is positive. The zeros of this polynomial are negative, Y here is positive. So beta is well defined as this construction. Now I have a little bit of time. I just wanted to show a little bit more some results that we get for the coefficients beta n, and because these results we could talk some about a little bit about the Sobolev polynomial, the behavior of the Sobolev polynomials, the asymptotic behavior, and also a little bit about the zeros. Just to remember here how is the connection between the two. the papers I told before from Ranga and from Paco and Ranga, they also had this bound for chi and beta. And also they proved that when n goes to infinite, beta goes to 1. But we managed to improve a little bit, and we managed to get some bound for beta n plus 1 in terms of using actually the minimal parameter sequence. We managed to improve it, not improve because here we have a bigger bound, but we could tell something using the fact that beta is here. For example, if we make eta goes to infinite, this goes to 0. Also using now the coefficients of the recurrence relation for the polynomials q and hat, we managed to find other bounds for the modulus here. Just a sketch of the proof from what they have before, Ranga and Paco. This is true. So we use some properties about the minimal parameter sequence. Actually, in this case, is every parameter of the for the chain sequence can be has to obey this rule and also this. So we managed to prove this, and then just using the fact how we know the explicit minimum parameter sequence for the first chain sequence, we got the first result. The second result actually is a very well-known method. We use the recurrence relation for Q and hat, and we divide by this quantity and multiply. Actually, the aim here is to get chain sequence here because it's written in terms of a parameter sequence here, and we get this for all y actually for all y positive, because the polynomials q also has this property that they don't vanish on y positive. So we use actually this d1 plus 1, that is this chain sequence, and here h that is the minimal parameter sequence. We have this property, and some result, for example, from Shihara, we know that when y is equals to 0, the minimal parameter sequence is always less than when we have y positive here. So this inequality produces this inequality. So now we can talk about when we use positive y here or 0 here. And when we put 0 here, we become just with the coefficients. So we have a bound for this ratio, and this ratio is exactly the one defining beta. But what interesting is, with this property, these bound properties, we could prove, for example, that when s goes to infinite, bn goes to this quantity that depends on the minimal parameter sequence. And as I told before, when eta goes to infinite, modulus of beta goes to 0. Also, we proved that when lambda goes to infinite, beta goes to 0. And we have used, also when lambda equals to 0, we managed to prove a little bit more. We managed to prove this inequality here. See, just thinking about eta can be real, but lambda is 0 here. And also when both eta and lambda are 0, we have these inequalities. The coefficients here are monotonically increases sequence. Okay, with these properties, it was not so difficult to prove that when eta goes to infinite, the Sobolev polynomials goes to this polynomial, z minus 1 to n. The proof is quite easy. We use this property and the information that the limit goes to 0. So we have that Sobolev and this polynomials goes to the same, but we know before that these polynomials are written in terms of the parorthogonal, it's some relate with parorthogonal polynomials, and we know it, so we managed to prove that this part here goes to minus 1n, and this part here goes to 0. Let me just show some pictures. Illustrating this behavior. For example, here we took Sobolev polynomials on the unit circle of degree 10. We fixed the lambda equals to 1, epsilon equals to half, and s equals to 1. And we increase eta. Eta equals to 1, equals to 10, and eta equals to 100. See that the zeros, the red dots are the zero. See the behavior here. And for example, here we see the behavior of the zeros accumulate in 1. That means that is exactly what we are, we proved here, that when goes to infinite, this Sobolev polynomial goes to this one. And also we see that here these polynomials have zeros inside the unit circle and outside of the unit circle. Other thing that we managed to prove using now that when lambda goes to infinite, beta goes to 0, modulus of beta goes to 0. But now here we have two cases. When epsilon equals to 0, the Sobolev goes to 1, z plus 1 to n, and when epsilon is different from 0, the behavior now, the Sobolev polynomial goes to z minus 1, z plus 1 to n minus 1. Let me show some pictures. I think, for example, here in this example, we choose epsilon equals to 0, eta equals to 2, s equals to 3, and we are variating lambda. See that in this case, all zeros of the Sobolev polynomial are going to minus 1, as we have here. In the other pictures, we choose the epsilon different from 0, and now we have 1 0 here as we increase the lambda, 1 0 going to 1, and the other are going to minus 1, the other n minus 1. So 9, here I have n is equals to 10, here we have n 9 going to the point minus 1. So in general, about the zeros, as you could see, we have zeros inside of the orthogonal of the unit circle and outside of the unit circle. That is always a good question, because we know that for the orthogonal polynomials on the unit circle, the zeros are all inside the unit disk, but the question is what we can tell about that. So we realize that there is no a rule, because we can see some zeros outside and some zeros inside. So what here we have red dots are the zeros of the polynomial, and black triangles here are the zeros of the derivative of the Sobolev orthogonal polynomial. What we managed to prove was when epsilon equals to 0, and also eta equals to 0, the zeros of the derivative are always inside the unit circle. But our experiment results seems that all, for the derivative, all are inside, but we are studying them now. But see here in these three plots, we increase actually S. And we see that when S is very small, all the zeros are inside, we increase a bit the S and the zeros still inside, but for some example, the zeros are outside of the unit circle. What we managed till now was to find some sufficient conditions for all the zeros of the Sobolev polynomial stay on the unit circle. Actually, we use the result from Perestrofer. Here, the notation alpha n b y here are the Vrblunsky coefficients for the polynomial, orthogonal polynomial on the unit circle, with respect to the measure mu b epsilon. So we construct this quantity, delta n plus 1 here, and if this quantity is less than 1, we guarantee that all zeros are inside the unit circle. So if we come back to the figures here, for this S, the delta is less than 1, so all are inside. Here we have actually a delta that is greater than 1, we have inside. But in this case, when S equals to half here, the value of delta is greater than 1, but we have all zeros inside. So we can improve, actually, we think that we can improve the sufficient conditions. What's more, we did, for example, for the case lambda equals to 0, eta equals to 0, and the epsilon equals to 0, the easiest case, we managed to prove that all the zeros of the Sobolev are inside the disk. Also, z equals 0 is also a 0 of this polynomial. And using some result, I will show later, we managed to prove that the zeros of these polynomials lie in a ring that can be written in this way, and also using a work of Safa and Varga, we can find the parabolic free region of zeros. So we have a parabolic region that all the zeros are outside of this. So the proof is not so difficult. We just can, for example, we have this expression, and then we can just, because this expression, we can write the Sobolev polynomials in terms of all polynomials phi b epsilon in this way. And now the coefficients here, actually they are multiplication of betas. In this case, for this case that we are dealing, the polynomial here is very simple, it's just z to the n, because we are talking about oh, sorry, I forgot the name now.
Lebesgue.
Thank you, Lebesgue measure in this case. So we can write it like this. We see that 0 is a root. And then, because this behavior of the coefficients, and using the theorem of Eneston-Kakea, that when the coefficients has this behavior, all the zeros lie inside the unit disk. And also here an extension of this theorem, also attributed to Eneston, tells that the zeros, we'll just remove the z, the zeros of this polynomial lies in this ring, but since we have here this range, the minimal here will be always beta 2, the maximal here is going to be always beta n plus 1. So let me just show some pictures for this special case. Here we have a polynomial of degree 12. We see that even when we increase a lot the S is the parameter in the Sobolev orthogonal polynomial. We have all the zeros inside. Actually, we proved that. And my last slide is this, where we choose here a polynomial of degree 15, and we draw here the ring where we guarantee that all the zeros are inside this ring. Here is the zero equals to 0. And also we draw here the parabolic region. See that this parabolic region, that there is no 0 inside it. So I think is this what I wanted to tell. Here are the references. Actually, we mostly use these references about this family of Sobolev orthogonal polynomials. Here just these polynomials on the unit circle. Then here the two papers that I told you before about Sobolev orthogonal polynomial. And all these results and some more results from this talk were published in this paper just, I think, 1 month ago. And also here some other reference that I mentioned. Thank you for your attention.
Okay, thank you, Cleonice. We have time for questions. Is there